about the enzyme kinetics. A lot of enzyme kinetics questions, which is not surprising. Okay, the first one. I go through the basics of different types of inhibition and how to recognize a certain type of inhibition. Go over some questions about mixed inhibition and what the approach will look like. So in this case, I think there are many different, I present a lot of different ways to look at that. I think the easiest way to look at that still is going back to the way that I draw the relationship, is that E plus S to ES to product and enzyme. If the inhibitor is binding with the enzyme at the same site as substrate binding, it has to be expressed this way. So that this will be either inhibitor binds or substrate binds. So that is will be a good representation of a competitive inhibition. Versus non-competitive is it can bind to free enzyme or ES complex. So then this will be a good understanding of or a description of non-competitive. And then we have E plus S, ES to product and E plus inhibitor at the ES. This is uncompetitive because inhibitor only can bind to the ES, not to the E. So that's sort of like consistent with the idea, the concept that the substrate must be binding to the enzyme, that is creating something for the inhibitor to bind. And that is the same thing as consistent with the idea of use fit as well. That substrate binds in the enzyme active site, cause a conformational change, now create a pocket or region, now uncompetitive inhibitor can bind. So without binding of substrate, no conformational change, no region for the uncompetitive inhibitor to bind. So the characteristic of this one is that we have to look at the equilibrium right here to see any change in the Km value. Because the Km value is related to the amount of ES, is inversely proportional. So if in the presence of a reversible inhibitor, if it is changing the ES complex amount, relative amount, then we know if the Km apparent is changing or not. If it's changing, Km must be changing in the presence of the inhibitor. So one way to look at this one is that it's competitive. Without inhibitor, this is an equilibrium established. Now introducing an inhibitor, something is binding to the E. Instead, not on this side, but then on the left-hand side. Binding to E, less E, shift equilibrium this way, ES should be less. So that's why Km is increasing. So we can see that the equilibrium shift this way in the presence of the inhibitor. Now ES appears to be less in the presence of a competitive inhibitor. Km must be increasing. Versus in the middle scenario, inhibitor, let's say, binding equally well to the free enzyme or the ES complex, equally well. Now we establish the equilibrium. Introducing a non-competitive inhibitor binds equally well on both sides. It's not shifting the equilibrium because it's binding equally well. That's the assumption. Then, no change in equilibrium, no change in Km. And that is in the case of pure non-competitive. And then for the uncompetitive, it is same token as the competitive, now binding to the ES side. Yes, that's right. Good question. So a lot of times in the when we have a discussion, the question is, aren't we talking about a Km in the presence of inhibitor precisely. But then, whenever we say in the presence of a reversible inhibitor, we say increasing Km, lowering Km, actually we are comparing Km and Km apparent, like that. So then that terminology sometimes confusing. However, I have to bear in mind which is the right is the change of Km. The apparent Km seems to be higher. What's the apparent Km? It's the Km in the presence of the inhibitor. Higher, what's it comparing to? Km. Yeah. Very good point. You have to remember that. So then, in the presence of inhibitor, in here, it will shift the equilibrium that way, because now suddenly we have ES binding from ESI. Shifting equilibrium this way, the ES seems to be increasing. So that's why the Km seems to be lower. And every time when we say this, it simply means apparent Km is larger than Km. Km apparent, same as Km. Km apparent is smaller than Km. And since we, I have that later on, but I think right now I can talk about that maybe more fitting. Ki and Ki prime tells us how well inhibitor binds to free enzyme. The Ki. Ki prime is how the inhibitor binds to ES complex. When I say I binds equally well to E and ES, that simply means, or not simply means, more specifically, I'm referring to Ki equals to Ki prime. If these two are equal, that means binding affinity will be equal, and that's how the equilibrium will change. But as we can see that we have two numbers, this can be equal, or this can be bigger than that, or that can be bigger than this. So then we have three scenarios now for the non-competitive, right? The three scenario is Ki equals to Ki prime, Ki smaller than Ki prime, Ki larger than Ki prime. And this is the one for the pure, these two will be mixed inhibition. That's how we have a scenario. Why? Because inhibitor has the Ki and Ki prime. Here, I think the question is also referring to with the change of the Km now. Let's look at the Vmax. Vmax is not changing in the competitive. Why? Because we are looking at the mass balance equation. Whenever we are looking at change of Km or the comparison of Km, not change of Km, change of Vmax, we are comparing Vmax value and the apparent Vmax value in the presence of an inhibitor. So that Vmax is only going to be achieved when we have substrate concentration very, very large. So then we're asking, when we have very, very, very high substrate concentration, can we have ET equals to ES when substrate concentration very, very large? If the answer is yes, then Vmax can be achieved. So now, if we look at the very, very high substrate concentration, hypothetically we can saturate all the free enzymes. We can also drop this term. So that indeed this two is true. That's why this is true. Vmax can be achieved in the presence of I. Why is it true? Because I and substrate binds to the same site, no matter how much I is there in the system, we can always hypothetically have a substrate concentration so much higher than an inhibitor that this one does not exist because they are competing with one another for binding. So then this can indeed be negligible when we have high enough substrate concentration. And then this is satisfied, so Vmax is the same as the Vmax error. If you use the same rationale to look at non-competitive and uncompetitive, in both scenarios, we have the ESI in both scenarios. The ESI cannot be dropped when substrate is very, very, very high in both cases. What does that mean? In non-competitive and uncompetitive inhibition, there will always be some enzyme containing the inhibitor. In the presence of inhibitor, it is not producing product. If not every single enzyme molecule producing product, Vmax cannot be achieved. And that's why in the presence of an uncompetitive or non-competitive inhibitor, Vmax apparent must be smaller than Vmax because always some enzyme is going to have the inhibitor in it because substrate cannot displace that. It is not the same binding site.
Dr. Chan?
Yes?
Let's say if you don't want to memorize all these things, just want to have a concept of it. If you look at E plus S, in the equilibrium with ES, if you look at them as just like, reactants and products, and knowing that, let's say if the I is binding to E, that means less reactant, that means pushing the equilibrium to the left and vice versa for the uncompetitive. Would that make sense? Like thinking about like I is binding to ES, that means less ES, so the equilibrium is being pushed to the right. So that's why Km equals, the Km parent is less than Km. Is that a way of looking at it?
The way I understand your comments seems to be very similar to what I explained at first, right? It's a shifting equilibrium. If you are adding on one side the equilibrium of E plus S, ES, if you're shifting equilibrium, changing, that's how you can affect
I was just
ES.
thinking about like stuff being consumed, like ES being, ES being a product. And when I is binding to ES, that means that's being consumed. That means we need more of it. That's why it's being shifted to the right. Is that a way of thinking about it?
If I'm understanding you correctly, if you look at uncompetitive inhibition, the inhibitor is binding to the ES. Because of that reason, then it will have less ES. That's why equilibrium shift to formation of more ES. That is correct. Yeah, that's the same concept as I used.
And the second question, if like competitive inhibitor at the end of the day, Vmax equals Vmax apparent, then what is the significance of having such an inhibition?
Good question, okay? Good conceptual question. The comment asking is that if in a competitive inhibition, the Vmax apparent is the same as Vmax. So what is the significance of that enzyme inhibition, right? Okay. Remember that in the presence of any inhibitor, enzyme inhibitor, the definition is that the rate of product formation decreases. You see that the definition? In the presence of an enzyme inhibitor, the rate of product formation is lower. What is rate of product formation? V naught, right? Does it have anything to do with V? Are we talking about Vmax? No. Vmax is a condition, a number, the highest rate of product formation that can be achieved. But a lot of times, enzymes operate at a rate of product formation. So then even though Vmax is not changing at the function of the enzyme, at that stage of the concentration, it is being affected. So it is the rate of product formation that's affected, V naught, not necessarily Vmax. Vmax will tell you what kind of inhibition, and that is informative as well. Ask a question, okay? Very informal. So, alpha value, and then I think this is more so referring to the line river plot. Okay? And then to look at how it is being drawn. So the way you look at line river plot is that this is without, let's say, inhibitor. The easiest way to look at line river plot is to look at the x-intercept and the y-intercept. Even though the slope want to tell you something, because the slope is Km over Vmax. But then it's a lot easier to look at x and y-intercept. Why? Because it's only one parameter that you're looking at. So the y-intercept is always 1 over Vmax. X-intercept is always minus 1 over Km. So we know that if we change this direction, Vmax is decreasing. So in the case of the enzyme inhibition, Vmax can, apparent Vmax can be either the same as Vmax or always lower. So it's always going to go up, never go down. Okay? However, Km, if you move this way, it is increasing Km. Moving that way is decreasing Km. So with that knowledge, now you can look at, judge any straight line. Let's say if we have one that is, I'm showing anyone, like this, any straight line. Okay. So what does that mean? That means this is, let's say, with inhibitor. That means that this inhibitor will give you a lower Vmax value and also a lower Km value. Right? That's what it means. So then you have to see, just by the x and y intercept, it will be very informative. In the case of, so first of all, let's go through the comparative, the easy one first. Comparative is without inhibitor with inhibitor.